Oh, really? Oh, okay. Sorry, then in that case, I shouldn't have hidden that. There it is. What I did before is I just like put this here. Sorry. Okay. Yeah. So, hello everyone. I'm Neda Hejazi. I'm a postdoc at the University of Kansas, working with KU Lab team. So I'm going to talk about the kind of vast topic, chemistry of embryos. So, you know that embryos are the most abundant stars in the galaxy, and they have lifetimes longer than the age of the universe. So, because they are not evolved, there is no change of surface abundances due to kind of dredge up process. Also, atomic diffusion process has a very, very kind of negligible effect on these stars. As a result, the surface chemistry of M dwarfs is a pristine signature of the chemical properties of their original molecular class. So the question is that can we use these amazing stars that have kind of very stable chemistry in like kind of distinguish or identifying different stellar population or different galactic components? The answer is yes. Why we don't have a large embryo of samples with metallicities from high resolution spectra, but even in the smaller high resolution sample, as you can see in the left panel, you can see that there are two different kind of metallicity distribution for tendus star and tectus star. On the other hand, there are large samples of MDRs with low resolution spectroscopy that has been proved to be very useful. And even you can see that stars with different metallicity ranges are separated very clearly. And even for the disk stars, more metallic stars in the tech and more metal poor stars in the more metallic stars in the tenders and more metal poor stars in the tectors are located in different regions. Another question is that can we use M-dwarf metallicity to probe galactic chemical evolution models? The answer is kind of is not very satisfying. So when the galaxy first emerges, this structure forms as star forming gas and dust fall into the central plane. But the simplest model, that is called simple closed box model, assumes that it happens at once, and after that there would be no exchange of mass between the disk or the system and external environment. But there's a problem. This model predicts too many metal pore in these stars, and as it is known as the GDR problems. But later on, it was observed in even K-dwarf samples or N-dwarf samples as well. So to solve this problem, we need to remove at least one of the very simple assumption. Recently, the models, like infall models or accretion models, has received much interest so far, especially those with declining rate. The declining rates. This slide shows two different infall models with declining rates, but with single episode. Both these models can mitigate the problems that are more matched with observation. that the simple closed box model, that the observation is metallicity distribution from the photometric calibration. But there's sad news that there are other models that can do the same thing, these models are very degenerate. So to direct this degeneracy, we need more information like alpha enhancement. So it is alpha enhancements versus metallicity for all low resolution spectra. And so in early galactic formation, when the stars are very metal poor, supernovae type 2 were the major source of enrichment, and they enriched the environment with alpha element. But after a while, when supernovae type 1a came into play, they enrich the materials or environment with a huge amount of ions that causing very sharp decrease in the distribution towards more metal-rich and younger stars. The same trend has been also observed in other samples with high-resolution spectroscopy, and even with other types of stars like giant stars or FGK dwarfs. They are both the same, showing the same trend. But if you look at the right panel, you can see something that you cannot see. It is not resolved in the left panel for low resolution. And it is here. There are two different populations, high alpha stars and low alpha stars. And also, this kind of bimodality has been observed in other surveys like Apogee, and again, you can see that for high alpha and low alpha. And it has been also shown that high alpha stars are related or correlated with thick stars, and low alpha population is related to the thin disk. So as a result, the one single episode of infall model cannot reproduce this these two population. So the two infall model with declining rates has been suggested. In this model, the high alpha stars were created in the first episode with very short time scale, and low alpha stars were created in the second infall with much longer time scale. And there is a very long gap, long delay between these two episodes. So but all of these models or these studies are based on FGK dwarfs or giants because of the lack of large N-dwarf sample with high resolution spectra. So switching to another topic, so chemical link between the planet and host star. So we know that the detailed elemental abundances can also help us to better characterize the exoplanet and to find out the planet formation processes. But it has shown that only a few elements like iron, silicon, magnesium, carbon, and oxygen are more relevant, and they can give us important information about the internal structure and composition of the rocky planet or even core of the giant planets. So the idea is that because the different stellar population have different chemical properties, they might have planets with different composition. It has been examined by calculating planet building blocks using the abundances of these 5 rock-forming elements and also another models. And so if you look at the left panels, the PDBs were calculated using abundances from observation of a sample of FGK dwarfs. And in the right panels, the same thing, but actually the PBBs were calculated using simulated abundances. If we just focus on our thin disk and thick disk, the both studies show roughly the same results, and so it means that thin disk stars have higher values of iron to silicate mass fraction and a lower water mass fraction as compared to the thick disk star. The thin disk stars are more likely have planets that have chemistry or composition similar to the solar planet in the solar system. On the other hand, thick star have a lower iron to silicate mass fraction that indicates that they have probably have a smaller core and have higher water mass fraction. That is indicates that they probably have a more oxygen rich. For all, JWST is measuring or observing the exoplanet with high accuracy, but unfortunately, majority of cooler JWST host stars do not have a measured abundances to better characterize their exoplanets. So it is the whole thing as we all these studies shows that we really urgently need to measure the abundances of M dwarfs or cooler stars. There have been numerous actually studies to measure the parameters of M dwarfs, but there's a problem because they are not even consistent to each other, even for individual stars. So you know that the spectra of M dwarfs are very complicated as compared to FGK dwarfs, and many kind of analysis like equivalent with analysis that can be used for more massive dwarfs is not applicable to M dwarfs. So the only thing we need, we need only to synthesize the spectra of the spectra. That is kind of a very huge task. So for our research, we have collected some kind of host star, including JW host star from iGreens instruments, and we have developed an automatic pipeline that can measure the abundances of cool dwarfs in a kind of iterative manner. The code will be publicly available very soon. In addition, we have also presented a technique to very carefully measure to carefully normalize the observed spectra. For our first study or pilot study, we applied our method to VASP 107 host star, which is a late K dwarf. And we measured the abundances of 15 elements. And recently, we applied this auto-spec fit to K218 host star, which is like an M dwarf. And we have measured the abundances of 10 elements plus some other kind of abundance ratios. So these are my summary, and for better to have better kind of discussion for this chemistry or chemical connection between planet and host star, please join us or Splinter and the Thursday. Thank you very much.
We have time for a couple questions.
No. Yeah, the Argin spectra, the range is for both H and K bands from 1.45 to 2.45 microns. Mostly, some 80% of the range is useful, but not, there are some bad pixel all the time, some kind of edge of the orders we need to remove them. So it's not 100%. Yes.
Let's think that again. And so for our last talk of this